Hello, good morning, and thank you for joining me in my shop. Today is December 8th. That's a special day for me. That's my birthday today. And what am I going to do about this console here? Record player and radio, I checked them out in the last video. I think I'm going to start with the radio. I'm pretty hopeful to get the radio operating properly. Record player, not so hopeful, I'm afraid. So I'm going to get that radio out of here and get it up on my bench, and we'll check it out. Okay, so I've got the record player out. So the record player is kind of in the way of the stereo here. Cord's tangled up. Just 1 second. There we go. So here we are. Here's the radio inside here. Sorry for the lousy camera work. And we've got some wires on the back to be disconnected, and then it's going to come out. Some bracket screws at the front. Okay, so sorry about the terrible camera work there. That stuff. So the record player can stay out and just wait for its turn here. Okay, here's the little radio, and it is a little radio. IF cans are tiny. Everything's small about this. Little guy. Great big console, little tiny radio. So that's the phono input there. Speakers are on a plug. They go in here, and obviously antenna and ground go there. And this is the input from the record player. Output. Now I tried turning one of these knobs, and I had a heck of a time turning it. This one here. This one. Wow! These are unbelievably stiff. Yeah, that's really, really stiff. What is that? Okay, we don't know. Bottom on it. Okay, we'll look into that in a sec. Everything looks fine up on top here. I don't see anything really weird. Oh, here's something weird. This wire. This wire is kind of not where it's supposed to be. It's not supposed to go down there. The side of it has been shaved. It's been down there probably since day one. Let's stick it over here. Okay. Quite fine. Let's take the bottom off and see what we've got here. The screw that you see missing here is part of a bracket holding the radio in. Well, I think I'm the first one here. I don't think anybody else has taken this out of the cabinet or done anything about it. So it has some interesting capacitors in it. All these look to be in great shape. There's a molded one here. Aerovox. So can't say I've ever seen capacitors look exactly like this, but these have been carefully manufactured, I think. Maybe they're a little higher quality than the others, I don't know. There's another molded capacitor here. The reason I'm pointing out these molded capacitors and these capacitors here is they tend to be in trouble, although they look pretty good on this radio. They really do. Now, what was so stiff about this? This is the tone control. It's probably stiff from bad lubrication in the shaft here. So we're going to just throw a little alcohol on it. That's not going to work. into these, and hopefully that'll loosen it up a little bit. Don't think anything else needs any treatment. Loosen it up at all already? I can't imagine. This is not turning at all. This one. Wow. Probably have to put some penetrating oil on them. Give them a little bit of time. Oops. Wow. Okay, let me grab the well-known and sometimes hated WD-40. Come on, it's just oil. Oil with a volatile component. So if you can turn these a little bit, then the oil or the solvent, whatever you're using, is encouraged to go down in, and often they loosen up real quick. Like, there we go. That's just loosened right up. But just now I can turn it with the finger. There's no restriction now at all. But if you can't turn them, it's very hard for the solvent to penetrate. That's why it's important to get this to turn even a little wee bit. There it goes. Just a little wee bit. And we'll leave it. Okay, while that guy is resuscitating on his own, we should hook this thing up and give it a play here on my bench, because actually I can't remember how well it worked. I don't remember. Something worth noting here is there's no internal antenna. I kind of expected there to be a loop antenna or a stick antenna here, but there isn't. So it's completely dependent on external antenna. I don't think I connected one up when I tested it. I certainly have to hook up a speaker. These are the speaker leads here. So I think what I can do, so I banged my microphone in case you heard a clunk there. So these are the leads to a speaker here in my shop. Okay, she's speakered. Now we're going to need to hook up the antenna here. So I have an outdoor antenna I use. It's not a wire antenna. It's called a mini whip. Look that up on the internet. Mini whip shortwave antenna or something like that. You'll find lots of information about these. Antennas, one thing they do is they send down a pretty strong signal. So even though I'm a long ways away from the antenna in my shop here, it's got enough juice to travel the cables, so to speak. Make it down here. So we'll leave this disconnected, but it's available now. We don't know is we don't know if this is switched to radio or to phono. Well, it won't really matter. It'll be obvious once we do this. Might as well put the last knob on. Have a complete set. Okay. And it's coffee break time here. Then we'll turn it on. Okie dokie, now I'm going to be plugging this in, but not straight into the wall. I'm going to plug it into this thing, which is plugged into this extension cord, which runs through this overly fancy looking panel here with two switches on it. It's coming from this guy, which is an isolation transformer with a variable output, and behind that is another isolation transformer, and don't ask me why. I have two of them. Probably not the best idea. I have a third one stored behind here, which I'm not using. Okay. Also, the power is going to get to this radio through these two light bulbs here. Well, one of them anyway. One is unscrewed, so the power is going to go through this light to get here. The idea of that, and this is an incandescent light, you know, with a filament. The idea of that is it will restrict the amount of power reaching the device under test here, and prevent something unfortunate from happening, like for instance all the generators at Niagara Falls coming to a screeching halt. We wouldn't want that to happen. Okay, a little practice session here. Is this the volume? Is that the volume? Just 1 second. You can see they are not labeled. There is no labeling. Oh, wait a minute. They are labeled. That's right, they're labeled on the radio. Yes. Yes, it is. So tone control is stuck. Okay, it's moving a little bit. Volume control is this one, it's fine. Okay, switch is off, and the selector switch is to the left. Okay, there we go. So watch the bulbs. Nothing. That's good. The set was turned off. Now I'm going to turn it on. Now this time when I hit the switch here, by the way, if I flip this switch down, power goes through the bulbs. If I flip it up, power doesn't go through the bulbs, goes straight from the Pickering nuclear power plant to here. Or is it the Bruce nuclear power plant that's driving my house? It's probably the Bruce. Okay. Let us hit the switch here. Oh yeah, I was going to explain the light. So the light should come on fairly bright. In the camera it's a little overdone. And then fairly quickly go down. Then sit maybe off where you can't even see it, or maybe just a glow, just the filament glowing, and then it'll brighten up a bit. As it brightens up, the radio may come to life. Okay, that's the plan. Here we go. So up, down, down, and then back up. About 15 seconds. Oh, this one's screwed in too. Surprise. No problem. We've gone down. We probably these probably won't glow at this point. And the voltage is 108. Almost the whole thing is there. Here it comes. Okay, dirty volume control. It needs to be. That's full tilt. Let's go back. Sure is quiet. Is that the radio? We'll go this way. No, that sounds more like a radio. There's no antenna attached. Okay, so we got the radio going. And the volume, yeah, it's skipping badly down low. Okay, we can fix that pretty easily. Why are we not? Okay, so we need an antenna on here. Let's fix the volume, because I got the WD-40 handy. Sometimes I do these live, sometimes not. Let's do this one. A little hard to make this stable. Okay, grab it by the volume control. They let you do that. Okay, so I'm going to spray. Oh, that's not, well, that'll do. That'll do. Spray through here. That's an opening right into the actual volume control mechanism here. Boop. Oh, oh. See, the crackling is gone. I hear something there. Yeah, I can hear a radio station in there. Okay, now we're going to give it the antenna. I think this is going to be working quite well, actually. Let's go with the antenna, and I'm going to put this on. Now, so this lead is grounded electrically. Right now, the radio is plugged into isolation transformers, and there's no ground. I hate to use the word reference. It's really quite confusing, but ground has nothing to do with this radio right now. But as soon as I put this on, the picture changes, and the isolation transformer no longer provides isolation. So I'm going to stick it on here. Nothing happened. What do we get now? It's a sports channel. If you look at the top here, you see the sliding piece. When I tune this slides, you can see the shadow of where it was sitting for how many years while dust and dirt collected on the top here. So this radio has not been played for or tuned anyway for a long, long time. Sports channel at 590. So assuming this tape here is correct, and no reason not to assume it, then we're right on the money. 640 here. 680 with the interference. Okay, next one will be 820. No. That might be it. 860, French station. So the reception is very poor at the higher bands. The higher. And notice while I'm doing this, that on this tape here, which is for the technician to do this kind of stuff with, because when the radio's out of the cabinet, there's no dial to work with. So this is the technician's dial, if you like. At 60, 90, and 1500, or 600, 900, 1500, the bars have been darkened. So these are almost certainly alignment points, where the radio needs to be tuned to an alignment point during certain alignment procedures. Oh, wait, it just went quiet and came back. What was that? Don't know. Maybe it's probably me. Probably an indication my coffee is running low. Okay, so it's working but not so great. We could run the tubes through a tube tester. Why not? Why don't we do that? We will run the tubes through the tube tester. I have to let them cool off there for a bit. Hey, that's a good time for some coffee. Okay, I think we're ready to go with the first tube, which is the rectifier tube, 35W4. I believe I've got the tester set up. Let me just 35WW4. Okay, first test is for a ballast that's in this tube, which I don't quite understand. But let's do it anyway. JR 0367 03670, and for the ballast test, this should be 0 also. And what we're looking for in this test is for the short light to come on every time I rotate this. Short test control. Okay. So it's not going to heat up. I think with this set to ballast, I don't think it heats up at all. And I think we can do the test right away. So watching the short light, on, 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 not on 2. Now, I think there's a fault inside my tester, frankly, because I think I can remember doing this kind of thing just recently and finding the second setting to be the third too. I wonder about that. Nope, there's the third. Yeah, so I suspect it's more the tester than it is the tube. Put this back here. Now we're going to set this up for actually operating the tube. The ballast thing is like a resistor as far as I understand. Okay, so we set this to, let's pull this out while we're doing this. 35 volts, JR 0507 0507 with a 0 on the end, 0 for the bias, 55. English, that's if we want to use the English setting and then replace in the good. Otherwise we can take an actual reading. So this is actually a rectifier test. So to do a rectifier test, this has to be in English. And then then you just depend on the good and the bad. Okay. Let's just go through the short test again. There's no flashing at all. Oh, no wonder. The tube's not plugged in. Okay, we'll give it a moment. Okay. Short test now. There's the flash. Flashing is okay. So if the light stays on, we're in trouble. No, light not staying on. So to test the rectifier, we're pushing P3 and we're watching. She's in the good. These tubes get very hot very fast, so I'm going to stick it back in the radio. I can feel it warming up. Okay, next tube is going to be the output tube. And picking that one, I picked the rectifier and the output tube as the two most likely tubes to be worn out. Not necessarily though. No idea the history. That tube says Rogers on it. So I'm pretty sure that's a replacement. And what is it? The other day I found the wrong tube in the output. This is a 50C5. 50C5. Is that the right tube? Do we have a tube chart? I don't know offhand right now, so I'll do the test and I'll check on the schematic afterwards. It's probably the correct tube. It's not likely to be wrong, but it can be wrong. 40C5, 50C5. Now that I've talked enough, I gotta look again. 50C5. 50 volts. On the filament, JR2763. JR2763 with a 0. 2391. 23 on the bias. 91 on the English. But we won't use the good bad thing. We'll take an actual reading here. So for this tube to show up good, The pointer should go above 4700. 4700. On the next scale up, 4700 is up here. So it's got to come all the way up to here to even be good. If it's anywhere down here, regardless of these words, the words don't mean anything when doing the test this particular way. Okay, double check. JR2763. JR27630. Good. In you go. Ooh, no. Yeah. 50. 50. Started thinking I'm about to stick a 6-volt tube into a 50-volt socket there. Tube would probably work really well for a very short period. Okay, let's look for shorts. Again, the light has to stay on. Flashing doesn't hurt. Okay, so this guy should test 4725. 4725 is right about here, way up there. Here we go. It's up good. So this is a good guy. He's a good guy. Okay, so that's 2 tubes done. 3 more to go. Now these tubes are like a tube set. You know, in the modern day we talk about chip sets, but they were tube sets. So I can almost guess what all these tubes are. I'm going to guess this is a 12 SA7. And what is it? It's a 12 BE6. Well, it's a good guess. 12 BE6. So I think the tube manufacturers weren't making tubes willy-nilly. They were trying to make tubes that would be attractive to the radio manufacturers to use and include in their stuff. Now, this is another Rogers tube. So Rogers is a Canadian company, very, very early on into radio manufacturing, and they were making vacuum tubes. Maybe people today don't realize that. We live around here because Rogers now is Rogers Cable TV. They're not making vacuum tubes anymore. They're not making electronic things anymore. They don't make radios or anything. They run the cable system. Big cable system. Okay, let's turn this down right away because I did see this was a 12, so we're going to put this on 12 before I forget. Now I'm going to dial up 12. I think it's this. 12 BE6. 12 BE6. 2 tests to do. First one is an amplifier. Try out an amplifier in here. So JR75623. JR75623. 11 and 63. 11 and 63. So again, this English setting is just to make the good bad work if you have the switch on good bad here. Otherwise, this is a reading meter. You read values off it. That's what I like to do. Okay, we're ready to plug the tube in. Check. 12. So if you took a 12-volt tube and ran it at 15 volts, nothing's going to happen to it. You run it at 20 volts, maybe. If you ran it a long time at 20 volts, that would be bad. I think you can read stuff about fooling around with the heater voltage briefly to try to reconstitute the tube. And, I'm not so sure that has any kind of longevity attached to it, even if it does work. Tubes wear out for a couple of reasons, but one of them is the cathode surface ablates as it operates and vaporizes very slowly, and eventually the special materials that are on the cathode to help electron emission wear out, and then the electron emission goes down, down, down. The tube gets weaker and weaker. That's usually how tubes wear out. Let's see if this one's worn out. Okay, before I push the button, JR7562. JR7562. 3, 11, 63. We're good. Any shorts? Ooh. What was that? It's just my wonky short testing thing here. Now this is supposed to, we're testing an triode amplifier 1425. So 1425 would be just about straight up, just behind the question mark there. Let her rip. Ooh, she's a little low. Yeah. So 1425 would be, and then 1425. No, 900 is the reject point. So 1425 would be like new, and 900, this is just around 900. So it's weak, but it's there. Now, we're going to test the oscillator side of this tube. So JR35627. JR35627. 0 and 67. 0. This just goes here, not that it even matters. P4 oscillator section. So this time the test should be 1600 for a good guide right up here, and for one that's time to go be about here. Good to go. Strong oscillator section. Very good. Ooh, weak on the triode. This pin get bent that badly. Bent pins on this too. Well, they're all bent. Funny. I didn't do that. Okay, in you go. Okay, so I don't think that would cause the radio to perform poorly. Now this one is the IF amplifier tube. Okay, let me guess. 12BA6. It's a 12BA6. He's won. Yeah, I won. Tell him what he's won, Jim. He's won absolutely nothing. Okay. And you can get that. Chicago 60609. Oh my God, how many of us have that number pounded into our heads? If you're a youngin', you don't know what the heck I'm talking about, do you? Okay, so 12BA6. Right here, one test. 12.6, of course. JR 35672. 35672. 9 and 83. The bias is important. This one's not so important. 3. Press P4, 2000, 3300. So we're on the 3000 scale. So if this tube is really cooking, it'll bounce the needle right off the end here. If it's cooked, then it's going to stop right around the 2000 mark here, or worse. Here we go. So the weather today, you probably realized I live in an area that's been hit with a lot of snow. We've got probably 2.5 to 3 feet of snow on the ground outside, and today it's plus 3 degrees and raining. Well, that's basically a disaster. Rain on top of snow. Not raining heavily though, but and then it's going to get cold in another day or two. I think it's just going to be a mess. Okay, any shorts in this tube? Oh, very weak flash there. Usually the tubes cause a couple flashes when I do that test, and when they don't flash, that can indicate a problem right there. 3, let's just double check. JR. Oh, I got a mistake here. How did that happen? This should be a 3. It happened because I did it. 3, 5, 6, 7. with a 2. Huh. Okay. I'm talking too much. That's the problem. Let's do the short thing again. It did not really. There. Now we're getting better flashes. Yeah. Okay. Good thing I checked that over. There we go. Got to get above 2,000. Above my finger. She's a winner. This one's responsible for a lot of the gain of the radio. Its ability to amplify a weak signal. Okay, well, there's only one tube left. Here he is. Should I take a guess at this one? 1286. I don't think so. Let's see what it is. 1286. Very close. Very similar tubes. Okay. Okay, 1280. Oh, really? 12.8 TUV. Oh, I gotta go to the other end of the roll. This is the problem. Roll chart. I don't know if I can make it. Get to the end of these. I don't think I can make it. I don't see 12 coming up here. I'm only at 7. Uh-oh. Jim, what did you do wrong here? Here's 12's coming up. 12. Oh my gosh. I have another list. Oh, there it is. I see it. That's right there. Good enough. Okay, I made it. Wow. 12AT6. Fantastic. Am I losing my mind? 12AT6. Okay, 12AT6. 12.6 JR 3702. 3702 with a 0. 3702. 18 57 quad loops on the Earthlink. P4. Oh, there's more than one test here. Oh, there's 3 tests. Of course there's 3 tests. Okay, so the first thing we're doing is the triode. The audio amplifier triode. Did I not? I pulled it to here. It is. Here it is. So this guy's job, he's got 2 jobs to do this too. One is the first amplifier, producing a strong enough signal to drive the output tube that will drive the speaker. So it's to produce enough signal to drive the output tube. And the other job, it has a couple of diodes in it, and the diodes are used to make the audio detectable in the RF signal. And that's what it's doing. Okay. That's why we got to do 3 tests. One for the triode we're going to do now, and then another one for one of the diodes, and another one for another diode. Here we go. In this case, 755. So we're on the 3000 scale. So it just has to get up above my finger here, and we're good. Let's do the shorts. No shorts. And P4. Ooh, another low one. What did I have to get up to? He says 755. So 755 is about there. Wow, it's right on the money. Okay. Let's try the diodes. So we change it now to 360. I can barely see the numbers. 3602. Just one number change. That's right. Just one number change. This drops 0. This goes to English. Pressing P1. And up here on the scale, right here it says diodes okay. We gotta get above that mark there. Okay, so everything's set, so we'll do the short thing because, okay, and we're pressing P1 diode. It's way above. So that is not a problem. Now the other diode is just 3502. 3502. 3502. Okay, that's all we gotta do. Select the other diode, do the short test because why not? And diode really okay. I'm going to do that triode test again. Is the diode test really good? Are they sharing a cathode? I don't know. 3702. 3702 018 57. Wow. Press the button and 7. Did I get this right? 755. 755. English. Put it there. Press the button. So we're right at the line. So if I put this on English, and if I set the English correctly, which I didn't bother doing, 57. Let's see what in English now. Replace or good. Replace that one. So tube testers to a large degree were tube selling machines, by the way. So you could show a customer this test, and of course they don't want to read the numbers. They just want good, replace. So it doesn't even say good, bad. It says good, replace. It'll help you sell those tubes. Great. So can this tube be responsible for weak operation of the radio? Weak audio. Oh, got a little hot there. Weak audio, I guess. Is that really the problem with this radio? I don't think so. I think I tuned through stations with a good signal coming in on the antenna and didn't pick much up. So that suggests either the alignment of the radio is off, or these components, these old components underneath, are dragging down its performance. Considering the look of the components underneath, I think I would be hesitant to start changing them out. And I would rather fool around with the alignment a bit. You know what? I gotta make sure I put this other. Oh, it's hot, it's hot, it's hot. That's why I left it. Circular thoughts. Do you find yourself doing that? You think your way through something, and then a moment later, you're back here thinking your way through it. You get a few steps and go, wait a minute, I just went through this. Yes, senility is coming. So if we want to align this guy, he's got a couple of alignment adjustments right there. And he's got these IF cans here. Yikes. It's unusual to see these little cans in these radios. And they're heavily waxed. So we can test the radio and find out if these are adjusted reasonably or not before fiddling with them. Otherwise, all we've got here is just the oscillator, the local oscillator adjustment, and there's going to be nothing underneath here, I don't think. Just making sure I didn't hide an adjustment. So there's really not too much to it. I mean, it's a single band radio. And the dial pointers seem to be quite accurate. So really, when it comes to weakness, if this is what's really happening, I'm sort of convincing myself it can't be alignment. There's just not enough alignment stuff to it unless the IFs are off. So that's what we'll do. We'll test the alignment of the IFs and judge whether they need to be adjusted or not after I drink some coffee. in order that what I'm going to do next makes sense to you, if you're not so wise about these radios yet, I'll explain a little bit. So I'm going to use my signal generator here. Okay, and you'll be able to read the frequency that we're operating at up here, and I'm going to set it to 455 kilohertz. 455 kilohertz. Okay, 455. And I'm just adjusting the output level on it. Very good. So we're going to transfer the antenna from antenna lead anyway, from where it was connected to an outdoor antenna. I'm going to connect it to the output of the signal generator. So we're going to feed this signal, 455 kilohertz, into the antenna. 455, that's not even on the AM band. The AM band starts at 530. 455 is a little ways below it. So what's going on here? So the fact is, I think few people realize how radios actually work. You might have a picture in your head that the signal comes in on the antenna, runs through these tubes, getting amplified, and when it's strong enough, they send it off to the speaker and you listen to it. Well, there's a few steps missing there, but the most important thing I think to understand about these radios is that really this radio tunes 455 kilohertz, and that's all. The only thing you can hear from the speaker is signals that are running at 455 kilohertz. Well, wait a minute. The radio's band starts above that, 530, and goes up. How can you ever hear anything? Well, you'd have to convert those signals you're hearing down to 455 kilohertz. How do you do that? So there's a trick that's played in these radios. First step of the trick is it generates its own signal. It has something called a local oscillator. And that signal is running a little higher than the regular radio band. When you tune a radio, and you see this capacitor moving in that, part of what's going on, actually the smaller one here, is it's changing the frequency of this internal local oscillator. They call it a local oscillator because it's local. It's here. It's not on my bench, and it's not, the radio station itself. It has its own little radio station built into it here, so to speak. Now, the funny thing is, if you take a signal, let's say a signal at 1,000,000 cycles per second, and you take another signal, let's say 100 hertz above that, so very close, but 100 hertz above it. So now you have these two signals. If you feed them through a device that has non-linear characteristics, what comes out of the device are two more signals. Now you got 4 signals coming out. What 4 signals? So you have the two original, so you have the 1,000,000 and the 1,000,000 plus 100, and you also get the sum of these two signals coming out and the difference between them. The difference is very important. So the sum of these two would be 2,000,000 plus 100. That'd be way up here somewhere. And the other signal, if you look at the difference or subtract these two numbers, it'd be 1,000,000 minus 1,100. You get 100. That's a pretty low frequency. I picked a bad example, but that's okay. You get 100. So there's a difference frequency available. So you have 4 frequencies coming out. One of them is the difference frequency. Now, let's say you're tuned to, well, here in Toronto we could tune to just above 1,000,000 to a channel called 1010 AM radio. Could tune there. The local oscillator, when we tune, that's what we're really tuning. We're changing this local oscillator up to a frequency which is exactly 455 kilohertz above 1010. So you have the 1010 signal, and you have some other radio signals floating around on the antenna coming into the radio. This is the one we want, this one here, the 1010. And then we have the local oscillator, which we can move around. As we move it around, there's a point at which the difference frequency between this and this guy we're after will be 455. And it's going to come out the speaker. We're going to hear it. If I move the local oscillator up, it could be now this signal plus the local oscillator. I shouldn't say plus. The difference between them could be 455. So in a sense, as you move the local oscillator up and down, you're converting these different signals one at a time to 455. And everything in between too. Everything's being shifted. In fact, I think in England they call this tube, we call it a mixer tube in North America, they call it a frequency shifter tube or something like that. Which is much more explanatory as to what it's doing. So the radio speaker only produces what's at 455, and the front end of the radio is busy converting the signal you want to listen to 455 kilohertz. The reason for that is because then the radio is very stable. This whole part I'm pointing to, this guy, this guy, this guy, they're all tuned to exactly that 455 kilohertz. When you tune the radio, you don't have to retune all this stuff. Consequently, the engineers can design this for maximum performance at 455. Plus, they stick an amplifier tube in here to boost it at 455. So that's what's going on in the radio. Converting, boosting at 455 kilohertz, and then the next tube down the way here is a detector tube. I won't bother talking about that because I've talked enough. Now to test this out, all we got to do is get a 455 kilohertz signal into this radio. It will go through these and come out the speaker. Or is it 450? Or is it 445? It should be 455. I haven't really checked. I haven't looked at the schematic for this radio yet. But they're almost all 455. So I'm just going to go up a little bit. And do this. I think you'll be able to see the numbers a little better. 454. Okay, so my counter's a little low. So that's good enough. That's 455 kilohertz coming out of the signal generator at a fairly low setting. I'm actually going to snap it up here. Slightly higher setting. The radio is not really intended to receive this signal, but nevertheless I can still push the intermediate frequency, that's what it's really called, the IF frequency, through the radio from the antenna. It'll find its way to this IF. The IF is tuned to the same frequency. Away she goes. We will hear it. Also, I need to turn on the modulation over here. So we have 1,000 hertz tone should come out of the speaker when this is at 455, if the radio is tuned properly. If it doesn't come out at 455 but it comes out at 440, let's say, then it's out of tune. There's a couple other things too we can discover along the way. So let's turn the radio on now. Turn on. There we go. In the end, if it turns out that it needs to be realigned, and it's quite possible, they'll have to deal with these waxed in controls here, and you know, wax is not like glue, wax is not like cement, so it's not the toughest thing to get past. Hello, let's turn it up. Bingo, there's the tone. So we know already this is close to 455, if not dead on. And just to prove to you it's this, you're listening to the tone from here, I'll change it from 1,000 hertz to 400. Okay. Now a lot of hiss coming out of the speaker too. Not sure how to interpret that. So I'm going to swing the frequency here up and down around 455. We're going to listen and see if it gets much louder somewhere else or fades out. It should fade out in either direction. We'll go up first, and it faded right out. We'll come back. Okay, now we'll go down. You see it's much louder down here. So 450. So what that will do to the radio, one thing it'll do is it'll cause the tuning to be out a little bit. Not much, just a little bit. It's a little out, but not a lot. Now, if you look at the top of the radio, you can see there are 4 different adjustments. 1, 2, 3, 4. Let me turn this down. We don't need the whistle going. Four adjustments. Each one of them has an independent effect on this signal. So you can think of it like four things, and you need to line them up. You need to get them lined up. Now, what if one is out of alignment? Well, the output will just be low, and the shape, although we're not looking at the shape right now, say as I tune through it, instead of going up and down, it might go up and down. I have a funny shape to it if I tune through it over here. Didn't notice that when I did it, but that could be the case. So just listening to it, all you know is you wouldn't even know it's lower than it should be. How can you possibly know? You can't really know without fiddling with these. If this had come up to 455, I'd probably say forget it. We won't do anything. And I have another way of testing this, and that's to pass. Let's do another test. Yeah. What we'll do is we'll set up a sweep test. And we'll sweep through. In other words, what you saw me doing here, doing this, I got a machine that'll do it automatically, like that. It goes fast enough that we should be able to get a nice display on my scope here. And we'll find out the shape of this response curve. Is it a nice thing? Or has it got a funny bump in it? Or is it flat on the top, or what? And that'll help judge whether it's worth cracking the wax on these IF transformers. Okay, you know what? It's coffee break time again. Okay, since I'm in the mood for explaining things, maybe I'll explain just a little more here. So we're going to start using this sweep generator, and I'm hooking the radio up to it. Now we're going to sweep through the IF frequency. We're going to start a little low and go a little high, so the signal generator will put out a sweep through the sensitive part of the radio. So first we need to check the start. Well, I got to turn it on. That would help. Check the start frequency. Maybe you can see it. 428. Let's make it 430. Okay, 430. So from 455, 430, that's 25 below, so I'm going to go 25 above. There's a reason for that. So 25 above 455, that's 50. Above 4, that's 480. So we'll start the stop frequency at 480. That's where it is. It's right at 480 already. Guess what I was doing with this last time. I'll start the sweep. Maybe we're going to hear something. Maybe I need to turn it up. What we should hear is a buzz. It could just be there's just not enough signal coming out of here. So there we are. Funny sounding buzz. I'm going to tune the radio a bit. Shouldn't change this. Changing it a lot. Usually it's a lot more buzzy, so I'm not so sure what's happening here. Let's turn this down. Okay, next thing is something I forgot about. So I'll explain what's going to happen here with the oscilloscope. The oscilloscope normally has an internal system that causes the dot to go across the screen. That's static electricity. Get a little thing out of the radio there. So, but we're not going to use the internal sweep. The sweep is going to come from this device. It's actually coming out on this cable, going around behind where you can't see it and showing up here. And that's what's causing this to go back and forth right now, or to go forth. It's a little off center. I'm going to leave it because as this thing warms up, it'll come back into the center better. If I set it up right, at this end is the start point, and at this end is the finish point of the sweep, and right in the middle will be the 455 frequency. And another way of kind of checking that, this thing manages to average it out. It's showing 454, so we're really close to it, but we're not seeing anything here. Now I have to put another signal into the oscilloscope, and ideally, I didn't think about this ahead of time, so I might have to stop a bit here. So I'm going to have to put these clips on underneath the chassis, and don't want to get hurt doing it. That's what it boils down to. So let me kill the power on the radio, and you have to look underneath it now. Usually a couple places you can get make this very stable. Not very stable. Okay, just keep that in mind. What I would want to look for is the detector tube, and attached to the detector tube, coming from it, should be a very large value resistor, which I'm just looking through the radio. Like the tube in question is down in this area. So I'm looking down here, and I'm looking for something like 2.2 megohms, but this is a bad way to do it. So a much better way to do it. That's a little random taking that approach. Look at the schematic, that would be helpful, but I haven't dug it up yet. So we can look at the tube involved. This was a 12 AT6. 12. It's probably going to say same as a 6 AT6. 12 AT6. Miniature type, used as a combined detector, amplifier, and AVC tube in a compact AC/DC receivers. This is a compact receiver. Identical to 6 AT6, so we have to go there to get more information, but what I really want to find out is just how the pins are hooked up. So we see a diode on pin 6 and a diode on pin 5. I think I'm going to have to look at the schematic here to be sure. You want to hook the oscilloscope up to, yeah. I'm going to have to dig up the schematic, so I'm going to stop for a bit and get that done. Okay, let's have a look at the schematic here. Philips PH202, that's the right number. And it even said something about Canadian somewhere. I don't see it here. So this is for sure the correct radio. This is pretty weird. Plate antenna. What is this? Curious. So they have this coil in between the antenna and the ground connection. So really, the antenna is energizing this coil, and then the coil is part of a transformer, so the signal moves on through the radio. So that's what's going on with plate antenna. Well, I'll look for that in the cabinet later. Maybe it's mounted in there somewhere. I've never heard of that, plate antenna. Very interesting, because this is kind of similar to the antenna I have outdoors, only the plate in my antenna outdoors is about 3 centimeters square, if even that. It's a little tiny thing. It's more like a point. Anyway, not to dwell on that. Just something unusual. So the tube we're concerned about is this one here. And we see the two diodes have simply been tied together. And if we track this back through here, we should come across a big fat resistor. There it is, 2.2 megohms right there. Now I want to get my connection, my scope, looking at this spot here. Now where's the volume control? Because the volume control often has exactly what I need right on the top of it. So let's just track back. What's this switch? Is it in the phono position? What's going on here? Well, the radio output is here, and it's showing not connected. I'll bet you this is in the phono position. I bet you there's a note on it too. Let's see. All DC voltage is measured to B minus with a 20,000 ohms per voltmeter. That's a fairly good voltmeter. With S2 in the radio position. Arrow indicates clockwise rotation of shafts of the potentiometers and the switch S2. Arrow indicates clockwise direction. There it is there. Little arrow. Very good. Capacitor values shown in a resistor value shown. System switch is shown as viewed from front. Screw connection on chassis. I don't see a note that says what I want. Should say something like radio shown in phono position. Well, I think we can be pretty sure of that. Really? Because phono. Where's the phono? Here's the phono input. Well, yeah, the phono input's connected through. Yeah, for sure. So this is in the phono position. We push it forward. What's going on down here? This looks like it's cutting off probably the screen voltage. Let's follow this along here. Yeah, going to the screen of the tube here. So closing this energizes the screen, and the tube will operate. So when you're in phono position, this tube is not operating, because all you really want is this guy here and this guy here. The rest of this radio is out of the picture during phono. Okay, we got that all figured out. So if this were pushed into the radio position, okay, dryer's done, then the signal, I see this capacitor is very important here in what I'm doing. So if I come to the top of the volume control, I'll be on the other side of this capacitor. Not a good idea. You really want to be over here. I gotta find this 2.2 mega ohm resistor somewhere near this can, this IF can. Okay, and if you're new to it, let's just run through this really quick. Right, antenna comes into this first tube called the mixer tube, but if we were in England, we'd have a smarter name, the frequency shifter tube. This is the one that where the local oscillator is generated down here, and it's mixed in with the signal coming in from the plate. Hey, what do you got on your plate today? And that's really not a good word to use here. And out it comes. Now it's mixed, so there's 4 signals coming up here. The original, the local oscillator, the sum, and the difference. The difference, if it's 455 kilohertz, will find its way through this tuned transformer, boosted through this tube, out through this tuned transformer, still at 455 kilohertz, and then wait a minute, something funny here. The signal goes to the top of the volume control. Wait a minute. Yeah, after being detected. Sorry, just my own confusion here. Okay, so the signal coming out of here is run through these diodes and gets rectified, and that's what enables the radio to recover the audio signal, which is then sent through the volume control, out of the volume control to this tube where it's amplified and sent over to this tube where it's amplified and sent through the speaker. Here's the speaker down here. This is a plug that plugs into this socket. There we go. That in really fast overview, that's what's happening. Received and shifted, amplified, detected, amplified, amplified, out to the speaker. Now, where am I going to hook up this scope? So I really want to get the output from here, but I don't want to mess the radio up. But if I go on this side of the 2.2 mega ohm resistor, I'm getting into a very high impedance circuit, which we really don't want to go there, because any additional, like hooking up a scope lead or something, will kind of throw things off too much. We can get on this side, that's a little better. But we'd be on here. Yeah, can we get there? And what is this? What is this combination doing? This combination is doing something special. I want to find this 2.2, find this point, find this wire coming out of here, probably leads me to the 2.2. Okay, I'm ready to go hunting. Let's go hunting. We will hunt. Now, by the way, did you notice on the schematic, which I'm sorry I clicked it off so fast, the tube that in this radio was a 12AT6. On the schematic, it's a 12AV6, and that's what I guessed. I guessed right. Now, this is a tube substitution handbook. So I can look up 12AT6, and you can see in the list here 12AV6. So they're very, very similar tubes. Not identical, but very similar. Okay, so we want to look at the second can. So terminals down here. Somewhere right around in here is going to be that big resistor. So we're going to take the close-up camera and go snooping around with that. And I'll apologize ahead of time for the automatic focus tends to hunt an awful lot. So again, so now we're looking at the bottom of the IF can, and we're looking now. What we're looking for is a 2.2. So that's red. So a resistor with two red bands. Standing on the cord here. Uh-oh, could be one of these. I have to do this differently, I think. So let's just keep going. No, looking up here. Hey, what's that? There's two red bands there. So that looks like red, yellow. That would be a 220K and not the one I'm after. Can't be too far. Oh, look at that one. There's another red, but it's red, yellow again. You're looking for red, green. There's a TV show, a popular TV show in Canada called The Red Green Show. Type that into YouTube and watch a little bit of what is pretty ridiculous humor. There it is. There he is. It's kind of ridiculous humor. Red Green Show. Okay. So again, thank you. Focus. So that's where I want to hook up. If I want to hook up on the right on that terminal, I'm looking at the output of that. You don't want to go on the other side. And then this thing here is probably a capacitor. I pointed to it like it was a resistor. It's probably a capacitor. Don't you know your stuff, Jim? You know what? I'm still confused about those things. Okay, I think that's the spot to hook up. Right there. Whoops, don't knock the radio over. Where's that look like? It looks like right. Good save there, right here. Okay. Get a proper scope lead here. I don't want to use the. I don't want to use this here. Scope lead has a ×1 ×10. I'm going to put it on the ×10. Now, good question. What do we do with the ground from the scope? So one option is to go onto the chassis. I'm looking in here. So there's a big capacitor right here, and it's connected to the chassis on this side. Anything else connected to the chassis? There might be a resistor. So I'm just looking for anything soldered down to the chassis, and there is nothing. So that means that the chassis is not being used as a B-. The B- almost certainly is at the other end of this capacitor. This is not switched on by any chance. So that's the ground. So this capacitor that's connected to the chassis, the other end of it is connected to what would be the outside of the capacitor, the filter capacitor. You see this big guy here with a cardboard tube on it. Yeah, like a cardboard tube like this. That's so you can't touch the metal. That's a safety thing. Likewise, not likewise, but yeah, I don't know why I said likewise. So that is the ground spot that I would want to hook that up to. Where'd it go? It made a break for it. Here it is. So what I'm doing is I'm connecting it to B minus. That's how you can. That's the proper way to say this. Okay, and then this is going to go on the terminal that has a lot of stuff hooked up to it right here. Okay, with this set to 10. Now the reason for the scope. Okay, can I just lay this like this? Yikes. Let's go like that. So I explained how the scope display was moving left and right, but I never talked about up and down. So up and down is coming from this lead now, and it's going to be based on the strength of the signal at that point. So you gotta imagine this now. I'm going to have this thing sweeping, the sweep generator rather. It's going to start below the IF tuned frequency. Nothing will happen. As it passes through it, the output will increase. The scope will reflect that up here. Will increase. When you get right on it, it will increase to a max. And then as you go past it, it'll come back down because you're leaving the 455 tune zone, and this will come down. So you end up with a look like this. Or it may go down. It's probably going to go down, in fact. That's the idea. Then we study the shape of the curve there and draw conclusions. So I think we're ready here. So first thing is turn on the radio again. Here we go. So I'm starting feeding it through the dim bulbs always, just to ensure that things are hunky dory. I'll leave it on because I'll leave it on the dim bulbs because 106 volts coming over should be enough. What happened to the sound? Did the wires pop off? I killed the power. No, they're still connected. It's possible hooking up the scope has killed the sound. It's possible. Back on. Regardless of it killing the sound, it was still should show up here. There it is. Right in the middle. Now, it's got lots of noise in it because the signal coming out of here is very, very low. So I'm going to make this less sensitive. I hear the speaker now. Okay, maybe I was too impatient before. So we're going to increase the output of the I have to relocate you here. So we're going to increase the output here. That's more what I'm looking for there. Okay, I'm going to turn down the speaker, or the volume. I'm going to turn up the brightness here a little bit. Make it easier to see for you. So this is describing a perfect shape. This is just lovely. Certainly is suggesting there's really no advantage to trying to adjust the thing. Just take a look at that. 1 tube trying to make a getaway on this radio here. Oh my gosh. So that was the output tube. That might explain something. Why the radio was a little quiet there. Okay, but that should not have affected the oscilloscope at all, because this is happening early in the radio. Actually, it's actually not happening so early. It's happening halfway through the radio. So, radio seemed to be weak. Well, we could attribute that now through basically a process of elimination that it's got to be a problem with components. Is the radio really weak, or am I just mistaken about it? The last thing we're going to do today is feed the signal and tune the radio, and just be sure that I'm not incorrect about it being weak. Okay, so I'm going to disconnect the sweep here. Antenna. I'm going to turn this down before I surprise myself. I'm going to hook this to the antenna. There's a chance yesterday when I was experimenting with the radio that the antenna was actually not switched on correctly. So I may have been listening without the antenna I thought I had. Now I know for sure this antenna is operating.
Okay, number 3. Billy Idol. Number 4. Carly Rage.
L'armée russe a une fille puissante, pendant que moi je suis avec ces civils à quartier, je reçois des messages de soldats qui sont juste à quelques kilomètres de la sur les lignes de front. Et je vais faire entendre les messages de nos deux, les Français et les deux.
Whoops. The reason I'm hesitating at this station, I tune this station in regularly and kind of use it as a check on radios. It's a French station. It's relatively strong here compared to other stuff during the day. There's some interference. I've never heard that interference before. I don't think it's from the radio itself. It's out there somewhere. I don't know. Okay, we'll move on. The real test will be to pick up. So this is 860 with the noise right beside it. So 820 is a Hamilton station. It's weak. Let's see if we can get it. There it is. You can't listen to that music for too long before you start bopping and feeling happy. Very happy type music. So, yeah, this radio's working great. It really is. 740 is right on the money.
Wednesday's high, just 2 degrees with rain and wet snow showers by the evening, and much colder for Thursday. Looks like right now highs could be closer to -4 during the day. Right now it is 6 at Pearson. Our guaranteed high is 7.
Pearson is the airport in Toronto.
And you know what I mean?
Radio's working quite good. Really good.
The 3 answers. We've been listening to Oil, the Irish want Alabama. Okay. In South Bend. Good luck, Jalen Monroe. Can't throw the football as it is. Good luck throwing it in 30-degree weather.
Well, so probably that's what happened. When I assessed the radio, I thought I had the antenna switched on. It was not switched on. So I got the idea that it was weak. So I've gone through all this process to try to identify where the weakness is coming from. But now I determined there is no weakness. It was all false. So, but in any case, it's kind of forced me to go through the whole radio and check out, tubes and stuff like that, alignment and the like. I don't think it's worth doing any work underneath here. I think, these capacitors are doing fine. I think there is maybe one more test we should do here. Just sticking my fingers into the radio. And that test would be the voltage of the grid of the output tube. One more test on this. And how do we do that? So we spot the output tube down here, and we need to identify the grid, and then we're going to make a voltage measurement onto it. And doing that, I will use I'll use this kind of meter because it's totally ungrounded. There's just no chance of a grounding error. happening. I'm mildly concerned about that. Okay, we'll put this here. Now I need. I can do this a couple ways. Let's look again at the schematic here. So we look at the output tube, and what I want to measure is the voltage. First, how have they biased this? So we're looking here and there. Okay. So it must be a cathode resistor. Here it is, right here. Why did I not spot it? 150 ohm cathode resistor right here. So to make a tube operate properly, you have to put a strong positive voltage up here. It's literally, and no, I shouldn't say this, but I will. It's sucking the electrons out of the tube, and the cathode is jamming them in. That's kind of how you can look at it. And in the course of moving from here to here, the electrons have to pass through these the screens or grid wires or whatever you want to call them. To make the tube work right, or the way they've designed the tube for it to work right, the voltage between here and the cathode has to be about negative, who knows, 10 volts or something like that. So you can push the grid down 10 volts, but that's tough because there's nothing to push with in a radio like this. So rather than push the grid down to make it negative, we'll raise the cathode up a few volts, and this will become positive relative to the B minus, and the grid will stay at the B minus voltage. And the result is you've now got a negative bias on the grid relative to the cathode, and the tube will work properly. What can happen here? This resistor can go high and the bias get too great. That's possible. It's not harmful. Loss of output volume and eventually distortion, especially on high volume settings, again, some distortion. So this is quite likely to have gone high, maybe not. But what's more likely is some charge is leaking through this capacitor. And this grid, instead of being at B minus potential or zero or ground, if you want to be reckless in your words, some of the charge will leak through here and build up on the grid, making the grid go positive. How does it go positive? Because there's a positive voltage here of 58 volts. I think that's what that says. Looks like 5.8, but I'm sure it's 58 or 50. 58 would be kind of weird. But some of that is the voltage here is pressuring across the capacitor. If any of it leaks through, grid becomes becomes positive, and ultimately the bias is disappearing between the grid and the cathode, and the result is more and more current flowing through the tube, wearing it out faster and faster, and you can't tell. You can't listen to it and go, oh, I know what's going on. That's not the case. So we need to test this. So this is interesting. In this radio, the capacitors are in good shape. So it's interesting to test this. I got to put a voltmeter on here and read the voltage to the B minus. And hopefully it's 0. If it comes back 4 volts positive, this capacitor has to go. Okay, we're ready to do the test. It's gotten very late in the morning here, but I do want to get this done. Okay, so the one thing I didn't do, I didn't take note of the pin number, so I will do that now. Pin number 2 or 5. 2 or 5 on this tube. 2 or 5. Okay. That's good. 2 or 5. So again, radio's off. Yeah. 2 or 5. So 1, 2. There's 2 right here. And 5. 5 is open. So they've used 2. And that's where we want to test. So I'm going to want to take this. I'm going to use a clip lead on the negative side because it's just, I don't have to pay attention to where 2 probes are, just where 1. So we'll connect this to the B minus point, which we know is down here. Very close to everything. Good. These clip leads have a way of jumping around, so I don't want that to happen. So I give him a little wiggle. I give him a chance. You gonna do something? No, he's gonna stay there. Okay, then this we're gonna want to put right on there, like that, and then we should read a voltage. It should be 0 if it's positive. It can't be negative actually. It's just not. There's no way it can go negative. Is that true? I don't know. Here we go. Everything's safe. Yeah. This may make noises come out the speaker too. And this is way too high. Okay, I can hear some sound. Make some noise. A little bit. So you see the voltage? 0. So this is a really good sign. What that says is the particular capacitor doing this job is in good shape. And it's indicative of all the rest of the capacitors. They're all in good shape. No reason to go and change them. The radio isn't even humming. It's fantastic actually. Okay, great. So that's it for this today. The radio passes all the tests. I don't have to do anything to it. That's one of the very, very, very few radios that have made it in here where I just say, hey, it's just fine. You could go and change all those capacitors if you wanted, but what are you really doing? You're taking the risk of damaging the radio, of making a mistake. There's little benefit to come from it. The capacitors you put in will not last forever either. So I don't want to do that, and you know, it's time and expense and all that kind of stuff. Fantastic. So tomorrow, record player will be back on here, and we'll do a number on the record player and see what we can come up with. So thanks a lot for watching, and have a great day. See ya.